So this is the last technique or method of proof uh, we're going to learn in this section, and it's called proof by contradiction. And the idea is that we can prove P implies Q by proving basically P and not Q imply some sort of ridiculous statement, R and not R. So just quickly as a review, we have three ways to prove things. We can P implies Q. We can prove it directly. So the idea is we assume P and somehow show that it does imply Q. We can prove it by proving the contrapositive, which means we prove not Q implies not P. And then finally, we can prove it by contradiction. This is the third method of proof, contradiction. And the way we prove P implies Q by contradiction is we assume P is true and not Q, and show somehow this implies some sort of ridiculous statement, such as some statement R being true and it being false. So R and not R. And remember that we've shown that these three are equal to each other logically. So that's why they give us proofs of P implies Q. So let's just look at a couple of examples, and we've actually already done these examples in the last video, but instead of doing it by using the contrapositive, we'll do it by proving it by contradiction. Okay, so let's identify our P and Q. So if xy is odd, that's going to be our P, and then our Q is going to be then x is odd and y is odd. And so that's our Q. And so if we want to do this prove this by contradiction, what we want to do is do P and not Q. And we want to show that this implies some other statement which we don't know yet. It'll become apparent in the proof, but we want to prove R and not R occur. And that's really the contradiction. So what's P, right? So let's just write this out real quickly. So P is just like P here. So X and Y is odd. So XY. So XY is odd. And not Q. So this is Q. X is odd and Y is odd. So and X is even, or Y is even. We'll kind of put that in parentheses here, so it's like this and that. And we want to show that this implies, and now we don't know what R is yet, so we'll have to find this out. We'll have to figure this one out. We'll figure this out as we kind of go through the proof, R and not R. All right, so here we go. So I'm going to write down proof. And we'll suppose, so let's first just let's let x and y be integers. This is sort of unspoken, but let's spell it out. So x and y are integers, and let's suppose this xy is odd. So x times y is odd. And I guess we should just do a comma here, right? So let's erase this. So xy is odd. Oh, I guess we have to do an and. And we want to say and x is even, so comma, and x is even, or y is even. All right, so one of these two is the case. And actually, if you think about it, it really doesn't matter which one we're going to assume is even, if x or y. So we can actually say something like, without loss of generality, we may assume x is actually even, because this proof will actually work either way. So let's say let's say that. So let's say without loss. Let's spell this one out. So without loss of generality, assume x is even. You could do cases for this, like case 1 would be x is even, and then case 2 would be y is even. That would be fine too, but we can do it this way because really the proofs will be exactly the same, you'll see. So without loss of generality, assume x is even. Then what? Then we can say x is equal to 2 times a, where a is an integer, and this follows by definition of even. And then we're going to do a notice that. So notice what? So what you're going to notice is if x is even and you multiply it by y, it's also going to be even. I mean, think about this. You know, if you have an even number like 4, it doesn't matter what number you multiply it by, it's still going to be even. So notice x times y will be equal to 2a times y, which is equal to 2b, where b is equal to a times y, and it's an element of the integers. Hence, xy equal to b is even. Which contradicts the assumption xy is odd. Therefore, xy is even and xy is odd. So that's the contradiction. So xy is odd. That was our assumption. And xy is even. And so basically then that's what tells us that this is a contradiction, and so we know that P does imply Q. So it turns out here that our R and not R was xy is odd and xy is not odd, which for us means xy is even. And so that's an example of a proof by contradiction. And so it feels a little bit strange because you really don't know what R is until you actually get to it. Let's do another example. All right, so here's another example we did in the last video when we proved this by the contrapositive. And so how do we do this? Okay, so again, we're going to let xy be integers, and we'll assume here, so 5 divides xy, and we want to show that 5 divides x and 5 divides y. Oh, I mean 5 does not divide xy, then 5 does not divide x, and 5 does not divide y. So let's write this down. So this is our P, and this is our Q. And we want to do this by contradiction. So what we want to show is that P and not Q will imply some sort of ridiculous statement. So R and not R. And we don't know what R and not R are right now until we actually do the proof. So here's the proof. So PF, proof. So we'll let x and y be integers. So we'll set it up. So it'll be an element of z. And then suppose And maybe I should write this out first. So let's write it out because I didn't do that. So let me move this down and let's write this out because it's good practice. All right. So what's p? P is 5 does not divide xy. So p is 5 does not divide xy. And then we'll have not q. Now not q, remember this is really De Morgan's law. So not this becomes an or, and so 5 does not divide x. If it's not that, then 5 does divide x. So 5 will divide x, or 5 will divide y. And we want to show that this again implies some ridiculous statement, r and not r. And that will be our contradiction. So suppose 5 does not divide x times y, and what? So comma, and 5 divides x, or 5 divides y. Now this one's kind of similar to the last one in the sense that we could do cases. Case 1 would be 5 divides x. Case 2 would be 5 divides y. Or we could say without loss of generality. So that's the shorter way to do it. So I'm going to say that. So without loss of generality, assume 5 divides x. Then what? So now we can say, by the definition of divides, if 5 divides x, that x is equal to 5 times a, comma, where a is an integer. And this follows by definition of divides. All right, so now what's going to happen is, if you notice, if you take x times y, you're going to see x times y is actually a multiple of 5. And so that'll say that 5 divides x times y. So notice, very similar to what we did before. So notice what? Notice if you take x times y, so x times y, that's equal to, and so we know x is 5a, so we'll plug in 5a here. So 5a times y. And then we'll call this 5 times b, comma, where b is equal to a times y, and that certainly is an integer because the integers are closed under multiplication. Hence what? Hence xy is equal to 5b. So hence xy equal 5b. Let's do this. So hence xy is equal to 5b implies, hence xy equal 5b implies 5 divides xy. But this contradicts the assumption five does not divide xy. Therefore, we get what? We have 5 divides xy, and 5 does not divide xy. And so you can see, oops, you can see I might have marked there. You can see in this case, let me copy this down, that what's our r? So our r, it doesn't matter which order you write these in, but our r in this case, you could say this is our r, right, and this is our not r, or you could flip them. It really doesn't matter. But that's the idea. So by contradiction, this statement's actually true.